So this is the comparative analysis of three system that we just discussed. That was the system 1, 2, and 3. As they were shown in table 6.4. Let me show you the table again for reference. The location of the system 1 at site 3 affects 33.33% decrease in power generation cost as compared to the site 1. The second point of consideration is that the location of system 2 at site 3 affects 34.15% decrease in power generation cost as compared to site 1. Similarly, the location of system 3 at site 3 affects 30.56% decrease in power generation cost compared to site 1. So we can conclude from this analysis that highest decrease in power generation cost when moving to a site with improved full load hours occur for system number 2. Secondly, deploying for system number 3 in favor of system number 1 at the site 1, the results that results in 14.29% decrease in power generation cost. However, it can be seen that deployment of system number 3 in the favor of system number 1 at site number 2 results lesser as compared to 14.29, that is 11.76% decrease in power generation cost. And the deployment of system 3 in favor of system number 1 at site number 3 results in only 10.71% decrease in power generation cost. So the conclusion on the basis of these are, second conclusion is the highest saving in power generation cost is obtained when the lower ranking power generator, that is was 2000 kilowatt system is used instead of uh, 2 kilowatt system at site number 1. So this is the chart that shows the resulting specific electricity generation cost for the photovoltaic generated electric energy, exemplary for site number 1. According to this diagram, the provision cost decrease with increase in installed plant capacity. This applies in particular to capacities between 1 and 5 kilowatt. For example, for 1.5 kilowatt plant powered by a multi-crystalline photovoltaic module, power production cost roughly will be around 0.5 to 0.6 euros per kilowatt hour. However, by installing a 3 kilowatt generator, these costs can be reduced to approximately 0.4 to 0.55 euro per kilowatt hour. With continuing increasing power capacities, specific production costs are even further reduced. For a 2000 kilowatt plant, they are still in the range of 0.34 to 0.38 euros per kilowatt hour. For a system with roof installed multi-crystalline modules, that mean real power generation costs are thus expected to be between 0.40 and 0.55 euros per kilowatt hour. That was the can be said that was site number 1. The illustrated range is due to regional radiation variation in middle Europe and to different investments for plants of the same capacity due to different technical solutions available in the market with different costs. The increasing capacity of photovoltaic power station specific power production costs are further reduced. However, the decrease in the decrease is considerably lower. For our 2000 kilowatt photovoltaic power plant, mean power production costs vary between approximately 0.25 to 0.40 euros per kilowatt hour under the circumstances that were discussed for the site number 1. For even higher installed electrical capacities, further reduction of only a few percent can be expected. The partially tremendously low specific power production costs for photovoltaic power systems plants in comparison of roof mounted solar systems are primarily attributable to lower specific overall installment cost, generally high mean annual inverter efficiencies, as well as optimum inclination and orientation that can be assured for the ground mounted solar power plants. So, electricity generation cost decreases with increase in plant capacity, especially for plants ranging from 1 to 5 kilowatt. And the shaded region, this is shaded region, represents for the cost of similar capacity plants due to variation in radiation and variable investment cost for different situation. So it can be seen that the cost relatively increases fastest for 0 to 5 region, let's say 0 to 10 and 15 regions, and it has a lesser effect when the increased electrical power ranges in thousands of kilowatt. So this is the overall summary. Yet, in particular cases and under different site conditions, power production cost may differ tremendously from magnitudes indicated in table 6.4 to estimate the impact of such influences on power production. This figure illustrates sensitivity analysis of uh, uh, predominant parameters within the variation of plus minus 30% using the example of 20 kilowatt photovoltaic system at site 1 based on a multicrystalline module taken from the on that table that was discussed. It was the, I think, table 6.4. Thus, beside the plant investment cost, the number of full load hours calculated on the basis of the system util utilization ratio and the effective radiated solar energy within the course of a year and the site condition has the most important impact on the power production cost. As a consequence, the cost of photovoltaic power generation can be noticeably decreased by reducing investment volume. For example, due to more cost coefficient cell manufacturing methods or enhanced plant efficiencies, for instance, achieved by the progress beyond the current state of technology. Operating cost and interest rate have, by contrast, only a minor impact on photovoltaic power generation cost. Solely, the depreciation period still has a certain effect on the specific production cost of photovoltaic power generation. The indicated figure reveals that the power production cost within the sun belts of the earth, for example, the southern Europe and northern Africa, due to solar radiation doubled as compared to the middle Europe, can be reduced significantly under such favorable conditions. Cost of electricity production with small scale photovoltaic system are already very less. They are approximately uh, up to 0.3 euros per kilowatt hour for photovoltaic power plants, and the production costs can be even less than 0.25 kilowatt hour and below. Progress beyond the current state's technology is dependent upon the type of the panels that is being used for the smaller power generation purposes. The operating cost and the interest rates have, by contrast, only a minor impact on photovoltaic generation cost. The depreciation period has still a certain effect on the specific production cost of the photovoltaic power generation. The Now, this is the analysis of the effects of varying parameters of system number 2 and site parameters of system number 2 at the site number 1. So first of all, it is observed that 10% increase in depreciation period results in the decrease of power generation cost from 0.41 euros per kilowatt hour to 0.385 euros per kilowatt hour, and that is calculated to be around 6.1% decrease. The depreciation period of service life for a photovoltaic plant being uh, 20 years. Uh, this is the point of consideration. It is considered to be 20 years. 10% increase in overall investment results in increase in power generation cost from 0.41 to 0.45. That means approximately 9.76% increase based on the investment being 78,000 euros per 78 in kilowatts. The next is the 10% increase in operation cost results in increase in power generation cost from 0.41 to 0.42 euros per kilowatt hour, and that means that 2.44% increase based on the operation. The base operation cost considered over here is 800 uh, kilo euros per annum. The next is the 10% increase in full load hours. The results in decrease of power generation cost from 0.41 to 0.37 euros per um, uh, kilowatt hour. That is around 9.7% decreased based on the full load being 800 hours per annum at 100% intensity. All of these are at 100% intensities. Uh, the conclusion of this analysis that 10% is increase in operation cost and interest rate result only in minor variation of the power generation cost at 0 at 2.44% and 3.66%, that is 2.44% uh, for the increase in operation cost and 3.66% for the increase in interest rate. The next is a 10% increase in overall investment, result in highest increase in power generation cost, that is 9.66%. Moreover, 10% increase in full load hours results in highest increase in power generation, that is 9.66%, and 10% improvements of service life results in 6.1% increase in power generation cost. The next is the consideration of decreasing the cost of the photovoltaic system. So the first point is that the cost decreased by reduced investment volume. So use of a more cost efficient cell management methods can significantly reduce the system cost. Moreover, the use of technology beyond the current state of the art, that is technology dependent. If we change the technology, there is a boom in the price depreciation and efficiency of the products. Uh, the second one is the interest rate or the operating cost that have a little effect on power production cost. Number third is the highest solar radiation reduces the cost significantly. So Southern Europe and African countries have lower photovoltaic production cost as compared to the Central Europe or the other areas which have relatively a lower radiance level of sunlight. The next is the environmental analysis. The consumption rate of the Earth's material, low consumption for the monocrystalline and the polycrystalline and amorphous silicon cell manufacture has been documented. Moreover, we have seen their construction cycles and methods. uh, indium and uh, tellurium are used extensively in uh, the CIS and CDT, cadmium telluride. Cadmium is also being used, and indium is used. So these are the earth materials that are basically used in the construction or manufacturing process of these solar panels. The hydrogen selenide H2SE produced during the manufacture of the solar modules, that is highly toxic. Basically it is non toxic, and it becomes toxic as it has contact with water vapors, and it produces sulfuric acid, and when it is basically deposited, or it is in the sand or soil, that renders the soil infertile, and basically it changes the overall pH and the chemistry of the soil. Moreover, the ground-mounted photovoltaic plants partially or entirely inhabit the use of the ground for other purposes. Uh, uh, for example, farmer agricultural areas. The low-frequency magnetic fields emitted by the photovoltaic components lower than those of the household appliances. The solar cell technology is considered the problematic due to high use of the materials like copper, tellurium, selenium, and cadmium, because uh, they they are basically uh, producing oxides when they are wasted in lands, and that waste is comes in contact with water vapors. Moreover, fires in buildings may cause burning of the solar panels, resulting in emission of cadmium, tellurium, and selenium oxides that can be very harmful for human health. The next one is the injury hazards due to the falling of photovoltaic modules resulting from improper roof mounting that may reduce the adhering to construction and operation standard. This is a normal thing for a solar panel, because like in our country, uh, the when there is a sandstorm or a strong windstorm, the solar panels that are not properly mounted on the rooftops, they can fall. uh, the that fall can either cause the property damage, or it might also fall on a person, causing a casualty. So next is the recycling of the photovoltaic cells. The recycling of the glass components are relatively simple, but recycling of other materials require highly sophisticated chemical separation processes. Cadmium telluride and CIS technologies may need processing before they can be recycled, so that the heavy metals that are associated with them can be disposed of properly. Recycling of classic photovoltaic modules included the following three steps. The first one is the acid separation of the solar wafer from the bond. The next was the transfer of frameless modules from the uh, ferrosilicon suitable for the steel production, and complete separation of modules into glass materials and silicon wafers. Photovoltaic modules recycling, still it is in fancy, so reduction of environmental plants is, will be possible in future.